So, as I mentioned in the previous video, we can find absolute entropies of substances by finding the heat capacity at constant pressure. We could also use constant volume, but usually constant pressure is used because that's easier to do, practically speaking. Find that as a function of temperature. If we take that divided by the temperature, right, this will be, if we sort of plot a function, Cp over T divided by T as a function of temperature, right, this will have some curve like this, and what we have to do is at a given temperature, say we want to know the entropy at 298 Kelvin, we integrate the area under this curve from 0 to 298 Kelvin, and that gives us whatever value our entropy is. Now, there is a little bit more to it than this. This is sort of simplifying the process, and so one thing that we have to remember is phase transitions. So when we'll talk more about phase transitions in this class, but when a substance goes, obviously it'll start in the solid phase at the lowest temperatures, and we integrate the heat capacity in the solid phase, but eventually it will melt. And there's going to be additional heat that's added to the system at that temperature that doesn't actually increase the temperature of the substance. And so we need to, there'll be a reversible amount of heat added divided by the temperature at which it melts, right? This is an entropy change. And the way we can measure at constant pressure the entropy of of this happening is we use the enthalpy of fusion, right? That is, by definition, the heat required to melt the substance divided by that melting temperature. So we'll write that as T fusion. So that just gets added in, right? Because this is happening at constant pressure, these two are exactly equivalent, and these are the same, just with different subscript, but it's the exact same temperature, right? So that will just get added in as an additional entropy that's added to our system because it's extra heat divided by temperature, right? It's just the definition of entropy. We're going to repeat that. We'll have our liquid phase here, and we'll integrate that until we get to boiling, right, the vaporization. And there we're going to have the same thing. We'll have the reversible heat divided by T vaporization. So we get the enthalpy of vaporization divided by the boiling temperature, and that gets added in. So what this will look like mathematically is we'll have, all right, so we'll have S at some temperature T. So we'll have to integrate from 0 to T fusion the heat capacity of the solid as a function of temperature divided by temperature. And I'm writing these as T primes because our generic temperature here is now whatever temperature we're going up to. Okay. Then we add in delta H fusion, right, the enthalpy of fusion for our substance divided by the melting temperature, the temperature fusion. Then we integrate from T fusion to T vaporization. Now this, depending on the temperature, we may not have all these phase changes here. I'm writing, this generically for solid to liquid to gas, but you may not need all of these. So the heat capacity of the liquid as a function of T temperature divided by temperature dt prime. And then we would add in the enthalpy of vaporization divided by the temperature of vaporization, and then we integrate again from that boiling point up to whatever temperature we're going up to. Then we'll have the heat capacity of the gas as a function of temperature divided by temperature dt prime. So we have this long expression, but this is really just saying that we need to remember phase transitions. And so what we have to do is then, right, so these are known, right, these we can measure, and you can often look these up in a textbook for a given pressure, or not necessarily a textbook, but somewhere, or you can measure it yourself if you do the measurements of the melting temperature and how much heat it takes. But then we need, the tricky part is getting these,
right, heat capacities for our different phases as a function of temperature. So in the next video, I will talk briefly about what an instrument that does this might look like.